All right. You good? Yeah. Good morning. My name is Nima Neghaban. I'm CTO of GIS Federal. This is Amit Vij. He's CEO. I'd like to thank everyone for having us here today. We're going to talk about our distributed database product called GPUdb. It's in the name. It's a distributed database that's centered around many core devices and the different kind of data structures and paradigm that that kind of approach generates. So, like I said, it's centered around primarily GPUs. We have worked with Xeon PHY cards before. Our best, most kind of production setup is using NVIDIA cards, but there's nothing stopping us from using other many core devices or ATI cards. Kind of a little bit of backstory. We were at on an Army project where basically we had hundreds and hundreds of different data providers needing to stream geospatial data in real time, constantly, to a set of user analysts who needed to be able to query across those schemas at runtime without any kind of indexing or any kind of need to work with the developer team, because it just would frankly take too long, and they needed to be able to iterate on that data quickly. So what came out of that was a need to say, let's have a geospatial processing engine that can do kind of big data scale, but with this kind of SQL style niceness that their developer set was used to, and that a user could easily understand and almost generate queries on the fly as well. Next slide.
And just a little bit of another background. So we've been incubated by the U.S. Army INSCOM. So a major initiative they wanted to have was to filter geospatial data, and then two main feeds are the tracking of entities, and then additionally fusing that with SIGINT data to do targeting on the fly.
Right.
So what came out was our computational engine, which is now getting into production and into Afghanistan.
So a little bit more backstory. That setup on that INSCOM project is actually running on UVs, each UV having 16 NVIDIA Tesla GPUs. So this is just, kind of hits on the themes that the gentleman from AMD talked about yesterday, which is basically we feel that the many core device, specifically the CPU GPU hybrid, is going to be a major growth sector, and largely because of these reasons. It's way less power, it's a lot higher density, and you're able to do really kind of unique and previously not really, thought of things as far as from a developer perspective and what you get as a user, especially an analytic user or a data scientist type user. So this is hitting on kind of what we've been talking about, but it also talks about the fact that our whole approach is to tie the threads that the many core device gives you to the data across the cluster. So it's about data availability, about being able to coordinate computation, and being able to give the end user a very simple query interface that they can naturally understand, so that they don't have to be a GPU expert, they don't have to be a cluster computing expert. They can just be your kind of regular DBA style user or developer, and can very quickly generate very powerful analytics.
So yeah, just another thing is, just in a nutshell, we're like an in-memory database, but we're accelerated by the use of GPUs. And then internally, we have a native geospatial rendering. So we don't have to give billions of points or geospatial points to another map server to render that data. We utilize the GPUs to render it on the fly. Because
we're constantly aligning data with threads, we can do, I believe what the gentleman before called property paths. We call it query chaining, where an analyst can take a query, get a huge result set that might be billions of points or billions of records, and then, once again, from that, do complex computations like a visualization of that data or a heat map visualization of that data. So we're going to show you that shortly.
Yeah, you can think of us as like a Oracle times 10 or SAP HANA, in which they're in-memory databases, but we're accelerated by the use of GPUs for the mathematical functions.
So we see it as kind of an evolution of that general idea, where if you have an in-memory database and doing kind of data structures and computations that work around the speed that memory buys you, we see it as the next step, where we're going to take that speed, align it with these thousands and thousands of threads, and give you a whole new kind of level of capability.
Difference, we're not customized with FPGAs. GPUs are commodity hardware, so it's very easy for customers with an existing cluster of nodes to just augment them with GPUs and have supercomputing power.
Right. We have some production users who have large, high memory footprints who are being able to just leverage what they already paid for by just adding GPUs. So again, this is hitting on this general theme that we're giving you more capability than the current kind of edge NoSQL players. We have a much smaller footprint, much higher compute density. One way to think about it that's different is, okay, you have like a MongoDB with an S2 sphere index, which is their geospatial index. And let's say there's 1 billion points in that index, and you ask for an area of interest, meaning the user drew some section on the map. And you'll get back that query from MongoDB, but you'll get the first 10 records back from MongoDB. And that will come back quick. But then if you ask MongoDB, okay, well, in that box, just actually count for me how many points or objects or records are in there, that will take upwards of, in our test, comparable tests, about 30 minutes. With GPUdb, because we're constantly tying threads with data, we can do massive parallel iterative computation and counting. So that will come back with GPUdb under a second.
So this is just a general case study, comparing CPU-based architectures to GPUs. So, NVIDIA released this from Bloomberg, and you can see the orders of magnitudes difference and the lowering of space, cost, and power. So just power alone is pretty staggering.
Right.
The cluster that 2,000 CPUs powering that cost $1.2 million reduces down to 31K. And once you go to the GPU type of paradigm, you can do many different types of calculations that were not fathomed in the CPU type of world. Right. So this is, we call this the Gandhi cluster. So basically what we did was we purchased 5 nodes. So we have 5 node clusters, and we have racks as well. But we bought used hardware to begin with. It was $870 and 72 gigs of RAM. So we like servers with a high degree of RAM, and then we augmented them with a 750 Ti NVIDIA card, which is cost $140.
So these are consumer grade cards. These aren't Teslas.
They're not even the K20s or the K40s. So for the Army, we went into production on a UV2000 that has 10 terabytes of RAM and 16 GPUs. And then we just got activated by USPS, and they have 16 UVs to track all mail. So,
and so
we can scale pretty.
Right. So we can scale, intranode and across an entire cluster, because it's very easy to add nodes, and it doesn't change the developer workflow or the data partitioning or anything like that, because the developer doesn't need to worry about partitioning their data or creating some sort of key sharding scheme. But the whole idea is we take all those kind of problems away, and those kind of things that make NoSQL, big scale data analysis kind of annoying.
So the demo that we're going to show you is going to be running off of this Gandhi cluster right here.
Right. So just quickly, this is another application that was developed by another development team. It's showing off GPUdb's ability to just generate and compute a heat map video based off of previous users' queries. So you'll see that basically what happened was the user made a series of queries, GPUdb generated that histogram and also generated a heat map time reference video on the fly for that user.
So these are tracks, basically. We get all the feeds from the UAVs, and then we can fuse this with the SIGINT data.
Right. And kind of to hit on GPUdb's geospatial heritage, it's the only database that I know about that has this semantic concept of track natively built in. So a track is an X, a Y, a timestamp, and a grouping identifier. And that's a native semantic type in GPUdb. We also have other native geospatial semantic types that make it kind of very powerful for geospatial processing, but you can also use it in any kind of traditional NoSQL style workflow.
Yeah, so we can render I mean, we basically rasterize PNGs, so we can rasterize a PNG in sub-second time. So naturally, our next progression was a video, and we can do this in seconds, uniquely. So you can say, show me all the tracks that are 36 miles per hour or greater and a white wagon with an attribute, and that's a unique query done at query time, and we can generate a video on the fly.
So that's the user basically, and we'll just jump in and show, but that's the user basically seeing an array of attributes that they know about, choosing one, and basically doing the query and then asking an advanced computation to occur. So there's no indexing, there's no knowledge of the data or the attributes in the data. The data is constantly streaming in by different providers, hundreds of different providers with their own schemas. So it's a little bit kind of like the properties that were hit on by the previous gentleman, where we don't try to fix on schemas and we're not doing any kind of a priori indexing.
So right here is 20,000 or 20 million flight tracks we got from ESRI, and they can't handle this data, and they utilized us for GeoInt for their cloud computing demonstrations this past year.
So what you're seeing right now is actually every time he's moving, GPUdb is generating a histogram, it's generating the heat map, and this is all through a thin client JavaScript web app. So GPUdb exposes a number of RESTful endpoints, and you can either send those RESTful endpoints Avro binary and get back Avro binary, or you can send in JSON and you'll get back JSON. So the JavaScript API that we have is all running through JSON, and this whole app, even though it's querying billions and billions of points, is just a set of JavaScript files. And it's getting back PNGs of billions and billions of points in sub-second time.
Yeah, so for mobile devices, downrange, they just download a 200 kilobyte PNG image for the result. But yet they have a handle to billions of points potentially.
Right. So what we use, we basically hand them, just like you would any other kind of database, a remote cursor that gives them the pointer to that set and the size. So you'll see right there's the size. So this one user is simultaneously making 4 or 5 queries, getting back the count, having the histogram generated, and having a heat map generated.
So before I clicked on a random location, you can see all the metadata here, and scroll through it for the different positions. Here, I can say, show me all the air, show me all the flights with the origin of LAX, and I'm going to just zoom out so you can, and once I click this button, it does a filter on the fly, and then you see the results from that query. And then I can do a time filter on top of that, and then instantly you see results.
So what you're seeing here is what we were just talking about, query chaining, right? That's the analyst doing a single query, then deciding, okay, that's interesting, I want to now keep drilling on that result set. So he did a time range filter query. And again, we also not only did that chain, we also gave you all the counts. And so now he just added another parameter to his query chain.
Show me all the flights with the altitude of that number right there. And
we have this concept of parent and child sets. A query chain can actually go across sets of different schemas. This particular demo doesn't really show that this much, but we'll show you the kind of admin tool and show you just basically how the data gets laid out, or how we represent it to the developer and the end user.
So I just switched from heat map mode to feature mode. So it's most of the time it becomes a big blob once you see so much data, but you can see the red dots are the track heads, and the blue are the trailing positions, and then the green are the actual tracks of the specific flights. But it's easier to see a heat map of it. So this database instance has multiple different data sets. So I'm going to shift into ships now. So this is 112 million ship AIS tracks. And then I can zoom in. I've never seen ship data like this, but you can see the actual paths that ships travel. And I can click on a specific location, and you should be able to get the metadata for it. Scroll through. I'm going to zoom out. So, you saw the metadata, one of the attributes. So we give you full handles to the different attributes of it. So I'm going to say vessel type, equals tanker. And then, very quickly you see 18 million positions with vessel type equals tanker. And I'm going to click on a location, get a handle to 6,000 results there. And these are all of type tanker.
And there's these AIS feeds, it's very easy to get these. And basically, it becomes very interesting to see, okay, you can find kind of very active ports. You can sift through the data and see what kind of products or ships or vessels are going to what ports, and you can glean a lot of business intelligence from just this with just this very simple application that's been developed.
So we have full text search capability built in as well. So I just did a full text search on oil, and then you see a good concentration in this area here. And if I click on that, you see a destination of oil. So we have multiple different ways to hit the data. Like I showed you before, it's attribute based, but then we'll show you this later on too, but you can annotate the data types and say what type of indexing or acceleration do you want to apply per column of the data.
So GPUdb by default gives you very intelligent kind of we call it like memory annotation or storage annotations, basically tuning how the data is stored from this tiered memory structure of VRAM to RAM to maybe high-speed disk like an SSD or a Fusion I/O, finally back to disk. So you can just take what the choices GPUdb does for you, or you can fine-tune it yourself. So now we're going to talk about show you Twitter data, and this will kind of give you an idea for this kind of streaming problem that we were facing at Army. So these are live tweets coming in.
So we're ingesting Twitter at the 1% feed entirely with this Gandhi cluster right here.
Right. So you'll see the count going up.
So now I'm going to do just a very freehand polygon that should be quite complicated. It hits our database. It says 355 million positions in there. So our data corpus right now is 1.7 billion.
The reason why he did it like that is a lot of kind of NoSQL geo processing engines work off basically like a geohash style system where different parts of their query result set needs to land in different buckets based on how they've cut up the earth, right? So he drew one that has no kind of common pattern, or it would hit so many buckets that getting that result set would take quite a long time, and you can zoom all the way in and out and get results very quickly, whereas your current NoSQL approach is really going around working off the geohash style approach.
So I just did an NAI filter, a named area of interest filter. I can apply a time filter on top of that. So here now I reduced that data set to 97 million, and then I can apply like Berg star, so like a wildcard text on top of that. And it comes back with 81,000 positions, and I can click somewhere close to New York. Then I get a handle to all the tweets at that location with Berg star. So within the military, we have OSINT as a data feed as well too. So I mean, it's an easy data feed for us to show to the public.
So it's easy to basically start to glean intelligence out of unstructured and structured data with these kind of combined capabilities.
I mean, we can do like current events if you guys are interested in current events, and say Ray and Bryce. I'm from Baltimore, so the football player.
So this is a Baltimore-based football player who was just recently in the news. So it's natural to think that there's going to be a lot of tweets about him. So you can see in the histogram there is an obvious spike on the day when the video came out.
So I just did like a 2-week filter, so now minus 2 weeks, and then I can click on some location and see the tweets related to that. So I mean, we can do current events, anything.
Try like ISIS.
So yeah, Vices. I mean, other companies, so PGE, we did a search on them, and you could see the work orders that they had that were concentrated in the near the California area. We have T-Mobile, Sprint, and Verizon. You know, naturally, we handle SIGINT data, so it's easy to handle their data as well. And they focus in on streaming data, so we can process that.
And in a lot of our production deployments, you have a lot of higher order analytics or machine learning algorithms using this as an input, right? So they're using GPUdb to do queries of multiple attributes at will, and then using that as an input into their higher order algorithm. So I mean, like for example, just here, just with a simple histogram, you can see ISIS and it building up over time in its kind of progression.
And yeah, I mean, we calculate the histogram too. So I mean, there's multiple different queries that are getting hit by the data.
Yeah, like we said, every time he's moving the mouse, he's generating about 4 or 5 different queries that are doing parallel computation across this commodity cluster.
And then if you guys want to see the features, that's 1.7 billion features rendered in sub-second time.
Right. So we're doing rasterization on the server side. We're doing visualization on the server side for clients. So you can be a thin client with a phone and visualize 1.7 billion tweets instantly because you're just getting back an image.
That's our presentation. Done early, so if you guys have questions.
I am going to be very surprised if there aren't any questions on this group. Do we have any? Panel 2? Any? What do people think here? Go ahead.
So we use Unix, we normalize, so on ingest, it's normalized to Unix epoch UTC. So that's up to the ingesting user to kind of normalize that. We see it, GPUdb sees it primarily as a double.
A question, what is this, and I think there are more questions out there, but what is the status for GIS Federal? I mean, with this, where are you going with it?
So we morphed it pretty much into a product-based company this past 6-7 months. We've been, primarily in the defense, and still are.
Yeah.
If you've heard of eyesight, we're the computational engine for eyesight from the Army side, and we're just commercializing this so for commercial clients.
Are you at this? You obviously have gotten revenue from. You're not at a pre-revenue stage. You're at a revenue stage. But are you in an exploratory stage, trying to find out what are the natural markets, or where are you?
Yeah, I mean, I think that sums it up pretty well. I mean, we have an existing kind of user base and kind of problem set, but we have identified that clearly. I think there's a lot of people that could be using this, and we're still trying to explore what are the right market segments to push to.
Okay. There's not. Do I see other questions? Yep.
I was wondering for the Twitter searches, when you brought up the example burger, there was a lot of text talking about a burger, but there were also a lot of usernames that had burger.
Right.
Can you distinguish between those?
Good question. So, this is our admin. So you can apply, like I mentioned, annotations to specific columns, and the tweet handle we index as well. So I did Berg star, so they would have Berg somewhere in their handle. So if I go to, so yeah, you want to talk about child?
Right.
Child as well?
So this kind of shows some of the graph-like characteristics of GPUdb. We're not a graph database, but to kind of give that ability where you have a single query being able to go against multiple data sets of varying schemas. So you've got hundreds of different data providers constantly ingesting, all with their own schema. They might be changing their schema, but you have one developer who's developed one query, or you have one analyst who has one query workflow that they like. You don't have to change anything because we take care of it via this parent-child relationship. So basically, all the data providers kind of dump each of their records into a parent set. GPUdb takes care of what children should be made, and the querying user queries against that parent set. So it decouples the need for the querying user to know about specific schemas.
So yeah, just like these, you can see the columns of Twitter right here, the data feed. So you can describe a column as text only index, or GPU accelerated, or GPU and text, or just store only. So so we can be very conservative in our memory usage,
Right,
and be smart.
Right,
in what
and you
to
can
allocate.
choose which, if you were doing a full text search, you can choose which specific columns, if you're just hitting a specific set, you can choose which specific columns you want to search against.
So we're not going to waste, memory usage on the URL of a tweet, and the text is only applied to the author and the text of the tweet.
So if I have a schema that has different column names, who does the equivalence?
The equivalence is done by the querying user, the querying developer.
So
Unless
I have to know what your internal schema is, and then map
so
my
in our next
columns
release,
to
we
that.
have we try to tread this semantic fine line. We don't want to get too far down, but you're going to have the ability to give concepts to attributes, and then equivalencies are going to come out of concepts.
What do you think, John?
I think they've got a pretty good system for accumulating a lot of data. Okay.
And this, you said this could feed into things like scoring algorithms that people
So
have or whatever?
Yeah, so it's used by a lot of higher order machine learning algorithms and analytics that need to generate feature vectors quickly and then perform some algorithm of their own.
Rich?
Yeah, you guys did this on a cheap 32-bit GPUs. Would there be any advantage to doing like a K40, 64-bit?
Absolutely.
Yeah?
A lot faster.
A lot faster.
Yeah, I mean, it's just basically faster. Yeah. We're just trying to show that you don't have to spend a lot of money, and it's all commodity, consumer-grade hardware.
Thanks.
Yeah, our production at the Army, we had K40s and K20s running on a UV2000, so that's $1 million rack. I mean, just on the hardware, and then it's for our computational engine.
Okay.
So this is a lot of data. What are you doing about the security to keep someone from hacking? I mean, this is data out there readily available, but...
So this is all public data.
This is Twitter data, yeah. I mean, this is public data that we can display.
Any place that's using non-public data is airwalled and very secure.
Okay, thank you so much.